Hello, I'm not sure if I'm supposed to start my talk.
Yeah. Hi, Apoorva.
Hi. Okay. I thought Professor Ghorpade or someone was supposed to be here. Okay.
Yeah, here, just the last talk has just ended. So we will, people, there are parallel sessions, so some people are moving to different rooms. So we'll
That's
start in a couple of minutes.
okay. Thanks. Okay, now I can see you. I could actually not see. The video was off, so I could not see you there. Okay.
I think you can see.
Yeah.
Oh, okay.
Now I can see Subir actually. Yeah.
Okay,
And
okay.
I can also hear you now. You were muted just now. Thanks.
Yeah, great.
And maybe I'll try sharing my slides.
So we 24 now. Yeah, let's start. Yeah, already last young. Okay, Apoorva, you are ready? All right. So welcome to this afternoon session, afternoon in India, that is, of the invited talk. And the speaker now is Professor Apoorva Khare. Again, many of you know him very well. He's a brilliant mathematician in the country, and he's going to talk about the topic where analysis meets algebra, or more precisely, Schur polynomials on the positive orthant. And I see that it's a joint work with Terry Tao. Apoorva, please.
Thank you for the invitation again to the organizers and for the kind introduction to Professor Ghorpade. Yeah, so in fact, this paper actually just got published finally this week. So it's, I think, my first talk after the paper actually got a volume and page numbers and so on. Okay, so this is, as he said, joint work with Terry Tao. This is about a concept that I knew as early as my PhD in representation theory called Schur polynomials. These are characters of some kind of very nice polynomial representations of GLN, in fact, or yeah. But I will be using them as functions. I will think of them as functions today, where they act, and I will look at their values and their behavior on the positive orthant. Okay, so without further ado, so let's define the players. So this Schur polynomial. So it's basically literally a generalized van der Waals determinant divided by the usual van der Waals. So if you have seen this, the theory of determinants, if you take n many variables and n distinct integers, and you take the determinant ui to the nj or nj minus 1, then this is an alternating polynomial in the variables, and therefore it is divisible by the usual van der Waals determinant. That's the theory of polynomials, and when you divide it, you get a symmetric homogeneous polynomial. That is called the Schur polynomial. You can define it over the integers and therefore over any field. Okay? This is one definition anyway. This requires the field to have, anyway, it can be defined over the integers and therefore specialized to any field. Notice that the denominator, as I said, is the van der Waals, and we will use this notation for it. V of a vector is just the product of uj minus ui's. Okay, so these are a very, very nice basis of homogeneous symmetric polynomials. They carry representation theoretic content because of the second point here. And they're usually defined in terms of a different way. And the advantage of this second way definition is you can define it over infinitely many variables or any number of variables. This definition here, which is due to Cauchy, is only defined for the same number of variables as the number of powers. But you can actually do this over arbitrary number of variables using the following definition. On the next page. Okay. And the representation theory content says, among other things, that if you specialize, so remember, of course, both of the numerator and denominator vanish when some ui's are the same. But of course, I cancel them out and I get an actual polynomial, and then I substitute 1, 1, 1, 1, 1. What I get is, I get the product of these differences divided by the product of j minus I. Okay. It's a ratio of 2 van der Waals again. Okay, so now let me now tell you about the other definition, the one that works more generally. So these are defined using semi-standard Young tableau. And so here is the idea. So suppose I want the Schur polynomial corresponding to 3 variables and 3 powers, 0, 2, and 4. So what I do is the following. Remember that I'm defining so ui to the 0, ui to the 2, ui to the 4, but divided by the van der Waals of powers as 0, 1, and 2. Right? So somehow I will be dividing out the 0 to 4 powers by 0, 1, 2 powers. You can imagine some kind of subtraction going on. And so when you subtract 0, 1, 2, you get 0, 1, 2 again. So I create diagrams with 0 cells in the bottom row, 1 cell in the next row, 2 cells in the top row. Okay, and all of these diagrams have the same shape. I fill them up as follows. Since n equals 3, I fill them up with numbers from 1 to 3. With the rule that the semi-standard part, these are called Young tableau, and I'm filling them up with the semi-standard rule, which is entries must strictly decrease as you go down every column, and entries can weakly decrease. They must be non-increasing as you go down every row. Okay, so here are all the 8 possible such configurations. Given the power 0, 2, and 4, I first subtract 0, 1, and 2 from it. It's called the staircase partition. I subtract that, and then I fill them up, those shapes, using semi-standard Young tableau to create those. And now it's literally very easy. The definition is you just add up the monomials for each of these. x3 square, u3 square u2 plus u3 square u1 plus u3 u2 square plus twice u3 u2 u1. There are 2 of these which have the same monomial, and so on. Okay, oops, what happened? So this is exactly this polynomial. You can check also that it factorizes in the following way. But by the way, this polynomial is actually corresponding to, in representation theory terms in algebra, it corresponds to the adjoint representation of the Lie algebra SL3C. Okay, and this is the 0, 8 space, and these remaining 6 guys are the root spaces. Okay, and these are the roots because this is the character of that representation. Okay, so that is one example. Here is another one. N equals 0, 2, and 3. So again, when I subtract 0, 1, 2, I get 0, 1, 1. So I just have 2, well, 0, I don't count 0 cells, 1 cell and 1 cell. Okay, and now entries must strictly decrease. So the only 3 possibilities are 3, 2, 3, 1, and 2, 1. That gives me my polynomial. So look at both of these polynomials. As you can see, they're all sums of monomials, right? So as I said, I'm planning to look at these polynomials as functions where the arguments take positive values, because this is the positive orthant. So when I look at these as sums of monomials and all the arguments are positive real numbers, it is clearly coordinate-wise increasing on the positive orthant, because it's everything is positive. Okay, so okay, that's what I say here. Fine. So now let's look at the ratio of these guys. Okay, so this is the numerator above, which I told you, divided by the denominator, which I told you, and everything again is on the positive orthant. So both of them are what we call monomial positive. They are sums of monomials, and they are in fact Schur positive, obviously, because they are sums of Schur polynomials, not just sums of monomials, but sums of Schur polynomials. In fact, they are each one Schur polynomial. So fine. And in particular, therefore, both of them are non-decreasing in each coordinate. The incredible fact, the surprising fact, if you will, whatever, is that the ratio has the same property. And notice that this ratio doesn't factorize. There is no cancellation or anything. It's just some ratio of 2 Schur polynomials. It has the same property. That coordinate on the positive orthant, it's non-decreasing. Okay. So the purpose of this talk is to sort of tell you about this fact in general, and then 2 of the applications. One that motivated it and one that came from it. Okay. So this is one of the theorems then, so that we prove. So for take any integer tuples n and m, not just 3 and 3, but arbitrary length of m and arbitrary length of n, such that coordinate-wise, this m tuple dominates the n tuple. The 0 is bigger equal 0, 2 then 2, and 4 over 3. Okay. Then look at the ratio of those Schur polynomials. This function is non-decreasing in each coordinate. And in fact, that's not the full power of our result. We prove that something stronger holds in terms of Schur positivity, which I will get to on the next few slides. But the statement is very, very clean and simple, right? Take 2 Schur polynomials, the powers above dominate the ones below, entry by entry. Look at the ratio on the positive orthant, and you have some very nice monotonicity, which is hence the title in the slide. Right? Okay, so how do I prove this? It's very easy. So for this specific case, I'm actually going to prove it for you. And look at, here's the proof. do the simplest possible thing. You want to show a function is non-decreasing. Use calculus that you teach to undergraduates. So take the quotient rule of differentiation, high d low, or I always forget, low d high minus high d low. That's what it says. And you see that what you get is in fact monomial positive. Again, it's a sum of monomials. And therefore, of course, if you plug in any positive real numbers, you get a non-negative or positive real number. So the derivative, I mean, the denominator is low square, so it doesn't matter. Since the derivative in any one coordinate is, this is being differentiated in U3. So therefore, the function is coordinate-wise non-decreasing along the U3 direction. But remember that this function is symmetric in all the three variables. So it's coordinate-wise not decreasing in every direction. It's just a symmetric function. Okay, but now, as I said, there was something stronger that was going to hold than monomial positivity. And what I do is, this function here is not symmetric in U3 now, because I'm differentiating with U3. But of course, it is symmetric in U1 and U2. So let me write it as a sum of powers of U3, and the coefficients are polynomials, symmetric polynomials of U1 and U2, right? And guess what? It turns out that these polynomials are in fact sums of Schur polynomials. Each of those coefficient polynomials is a sum of Schur polynomials. So here, for example, U3 multiplies is dividing the whole thing. So there is no constant term. U3 is the linear term, and I would put 2U1 U2 times U1 plus U2. That's this here. But you can check that that sum of monomials is exactly this. So it's exactly a sum of, it's twice a Schur polynomial. And the other one is U1, U3 square has coefficient U1 plus U2 square. That is U2 square plus U2 U1 plus U1 square. That's a Schur polynomial plus U1 U2. So every single coefficient is indeed a sum of Schur polynomials in the remaining two variables. And that's the Schur positivity phenomenon that one can prove in general. And so that's what one says. So in general, for general number of variables and number of powers, again, assuming these coordinate-wise dominate the denominator powers, again, do the same thing. It's enough to show by symmetry that one derivative is coordinate-wise non-decreasing, or sorry, is non-negative. And well, again, so this would follow if that expression, that this expression here is monomial positive. But in fact, we show that you can look at the coefficients of every power of un, because that's the asymmetric variable, and each of those is a Schur positive polynomial in the remaining variables. Yeah, so this is true completely generally. The key ingredient in this is actually a very deep result in sort of symmetric function theory or representation theory by Lamb, Postnikov, and Pilyavsky in 2007. And in turn, that emerged from Skandera's results on determinant inequalities. And I mentioned Skandera partly because, of course, the original inspiration was sort of his results, but also because the next application that I tell you, the first one, will feature Skandera again. Okay, let me ask if there are any questions. Just a minute. Okay, so if not, then let's continue. So far, as I said, this was the result. I'm calling it the Schur-Van der Monotonicity Lemma now. The point is, earlier I was talking about Schur polynomials, so integer power Van der Waals determinant divided by a usual Van der Waals determinant. Now I talk about the Schur-Van der Waals lemma, so I say I can take real powers. I don't even need integer powers. I don't even need them to be positive. They can take arbitrarily many real powers, the same number, of course, and such that coordinate-wise, the numerator powers are bigger equals the denominator powers. So the same result holds. Consider the function. So now I cannot consider it on the entire orthant, because you see, this is a ratio now of two different. It's a Schur polynomial by a Schur polynomial, which was a generalized Van der Waals by the usual Van der Waals divided by another generalized Van der Waals by the usual. So the usual Van der Waals cancel, and I can just look at this expression. If I don't assume that it's a polynomial or something. So then these are real powers. The arguments in U are strictly positive, but now I must assume that the arguments in U are coordinate-wise distinct, so that these numerator and denominator are defined and non-zero. Right? So the function is defined. But again, the same result holds. Look at this function, and this function on this subset of the positive orthant is indeed coordinate-wise non-decreasing. How do you prove it? Well, this is fairly straightforward. Now, once you know the deep result of Lamb, Postnikov and use it to prove the integer power version of this result that I told you about, this result is sort of, it's clearly more general because it holds more generally, but actually it's the same, it's equivalent. Why? Because I'm going to deduce it from the integer power result. So first multiply by all these coordinates which are non-zero, positive, taken to some negative power. So because of that, you can just remove all the, everything gets replaced by mj minus n0 and nj minus n0. In any case, all these powers become non-negative. And now secondly, you can always permute the rows and just the rows or just the columns in both the numerator and denominator, so that the entries are arranged this way. These are all positive numbers. And now let's first assume that they're rational. In that case, you see that you can take a common denominator for all of them, and then you basically reduce it to some Vandermonde times a ratio of Schur polynomials. And since the ratio of Schur polynomials is coordinate-wise non-decreasing, you get the same thing for the original function. This only works if the powers are rational. But now it's very easy. Just for real powers, you just rationally approximate and you're done. Monotonicity stays monotonicity, right? So that's how you do this. Okay, so anyway, so the point is this kind of a statement is sort of completely general. It doesn't care about the powers being integers, powers being non-negative. It's completely general as long as the entries of the function, the arguments, are pairwise distinct. Then it's non-decreasing coordinate-wise in every coordinate in the positive order. Okay, so now that is the first application. So, sorry, that is the lemma itself and sort of the 0th application, if you will, to an equivalent but a priori more general-looking statement. So now the next application is this. Okay, let's look at this example, right? So I know that this is coordinate-wise non-decreasing. So if every single argument ui or uj, whatever, is bigger equals 1, then this ratio is bigger than this evaluation at 1, 1, 1, 1, 1. And here, because the entries are equal, I'm just taking Schur polynomial. So there's no problem in defining these ratios. Right? And now this is, as we said, this was the Vandermonde of the M by the Vandermonde of the usual staircase, and the same thing here. So those Vandermondes cancel, you just get this. So clearly, whenever M dominates N coordinate-wise, let's say non-negative integers, this ratio of Schur polynomials dominates this ratio of the Vandermondes of the powers whenever the arguments are all bigger equals 1. So you can ask, of course, is the converse true? Is this inequality over this part of the orthant only the only possible when M dominates N coordinate-wise, or are there other tuples for which this inequality holds over that part of the orthant? Okay. Interestingly, the answer turns out to be that we can fully characterize that again. And so again, I don't need them to be integer powers. Or non-negative, I can take real powers. And so given the real numbers, again, the following is equivalent. Now I don't require coordinate-wise domination, right? We have that so now I would have to replace this inequality by using the determinant of the Vandermondes. So I do that. The determinants of the generalized Vandermondes, that ratio beats this for all distinct tuples again. So I put the not equal sign, unequal arguments. Meaning you look at the biggest index of M, that's of course bigger than the biggest index of N. Then the biggest two indices of M, add them up, that's bigger than the sum of the biggest two indices of coordinates of N, and so on for every single one. If M dominated N coordinate-wise, then this condition is trivial because every term here is bigger than every term there. And so their partial sums are bigger than the partial sums. But even if M doesn't dominate coordinate-wise, but these inequalities hold, that's good enough for this inequality to hold on this part of the orthant. So that's the statement, that's the theorem. The proof of this uses some kind of, okay, well, here you go. They use kind of growth estimates. We isolate kind of the leading term of a Schur polynomial, like a first order approximation. We use some kind of growth estimates for Schur polynomials or for Vandermonde determinants, either way. One uses the Harish-Chandra-Isaacson-Zuber integral and some Schur convexity result, maybe even due to Schur or somebody, I forget now. But it's found in sort of, I guess, Ingram Olkin's like massive tome on inequalities and majorization. Right? So in there, we found some result in some appendix, and that did the trick. So this is an if and only if characterization, a new characterization of weak majorization of real numbers using symmetric function theory. So that's the kind of flavor of this talk where algebra meets analysis. I'm talking about inherently algebraic objects. These are characters of polynomial representations of a Lie algebra or a Lie group. And they turn out to be, if you think of them as functions on the orthant, they turn out to characterize weak majorization. Okay. Now, sort of a more famous version of a variant of weak majorization is majorization, like in the Schur-Horn inequalities and various other places. So this problem, in fact, so we did not come to this problem of weak majorization directly. Somebody else had studied majorization through the framework of Schur polynomials, and that was again Skandera. So his name features again with Cuttler and Greene and Suvritsa of MIT. So they had studied this not too long ago, and again they only studied for integer powers but on the entire positive order. So what Skandera and those people wanted was this inequality should hold on 0 infinity to the n. So again, I'm looking at Schur polynomials on the entire positive order. and this was their theorem. They proved one implication and Sra proved the other. So we again have an if and only if. Fix integer powers, non-negative integer powers like this, then the same inequality holds. The ratio beats the value at once for all u in the entire orthant, not just the logarithmically positive orthant, not just bigger equals 1, but 0 infinity to the end. If and only if now you get majorization. That was a characterization of majorization proved in one direction, and then the other direction was proved by Sra in 2016. And luckily for us, because our paper came out in 2017 as a preprint, and so we just had access to that, but just about a year old. Now the point of again, majorization is just that it's weak majorization, plus the fact that the total content is the same. So the top entry is bigger than the top entry, the top two add up to bigger than the top two, and so on. And the entire terms of ni's, when you add them up, is equal to the entire sum of the ni's. That's the total content, or mj's. So that's majorization. Now I'm going to actually prove for you this statement, but replacing integers by any real numbers. I don't need these 0 less equals, of course. I don't care about that. And instead of the ratio of Schur, I would of course replace by the ratio of the generalized van der Waals determinant at unequal argument. So I don't even need 0 infinity to the end. I need 0 infinity not equals to the end or something. Right? So I'm going to do that on the next slide. So natural questions, right? Does this integers, can they be made real? And can we use a smaller subset than the full orthant? So I'm going to do that as well. I won't even use 0 infinity to the end with not equals. I'll use smaller parts of that. And the answer is yes, yes and yes. So here we are. So given first of all real numbers, I don't care about integers. I don't care non-negative or not. Sorry, yeah. First of all, so I replace the ratio of the Schur by the determinant. So this determinant ratio beats the ratio of the van der Waals for all distinct tuples. If and only if this determinant ratio, the same inequality holds, but now instead of looking at the full orthant, I just look at all coordinates less than 1 and all coordinates bigger than 1. I can even go much smaller. I can go to a countable subset of this and a countable subset of that, but that's getting technical. But I'll just tell you that if you look at two of the, so I'll divide the orthant. I take this positive orthant and I take logs. Then I again get Rn. So logarithmically, it's the entire real space. This is the logarithmically negative orthant and the logarithmically positive orthant inside the numerically positive orthant, right? So if you look at just these two opposing orthants and you look at this inequality holding there, that's good enough as to say M majorizes. So clearly, okay, 1 implies 2 is obvious because it's a smaller set of conditions. 3 implies 1 is if M majorizes M, then this happens. This is what Sra kind of proved. Our proof goes along the same lines. It's the 2 implies 3 that I want to tell you. Why does working on this two or these two logarithmic orthants imply the majorization? And that's a cute, nice observation in itself. So if U is in 1 infinity to the end, then as I already told you, what we proved was weak majorization. So M is weakly majorizing M. Fine. If U belongs to the logarithmically negative orthant, I look at 1 over U's. And in that, you can check that what you get is exactly, it's U to the M over U to the N. But that is the same as b to the minus m or b to the minus n. And I didn't care in my in the result I told you for weak majorization. These guys could be any real powers, positive or negative. So if this beats this ratio of van der Waals, then that means by our preceding weak majorization result, you get the inequality for weak majorization for minus m and minus n. So I have these two tuples of powers where m majorizes n and minus m weakly majorizes minus n. If you take the two facts together, that is if and only if m majorizes. So that's the proof for 2 implies 3. So we can just use our result and get this direct. 3 implies 1 is one has to use this Harish-Chandra and Zuber integral and so on. That is one sort of application. Let me again pause if there are any questions at this point. And then I will finish with my last application, my second and last application of that Schur Monotonicity Lemma. Okay, so then let me continue. So why did we come across or try to prove the Schur Monotonicity Lemma in the first place? So what we were trying to do is something that I have been working on. That positive on the entry wise. And specifically, with tau, we were looking at polynomials, so not just arbitrary functions, but polynomials acting entry wise. So let me just give some definitions. A real symmetric matrix, always real and symmetric in this talk, is positive semi-definite if all eigenvalues are non-negative. Equivalently, and that's the defining condition, the quadratic form that it induces, this matrix induces, a vector u going to here, is positive semi-definite. Hence, the matrix is positive semi-definite if the quadratic form is. That's the definition, but it's equivalent to say that all its eigenvalues, which are real by the spectral theorem, are non-negative. Okay. Given an integer size, dimension n, and a domain I, that Pn of I denote the n cross n positive semi-definite eigenvalues to lie in I want the entries to lie in I. In exactly the following manner. F square bracket A is equal to f of Aij. Normally you put f of parenthesis A, but then that's when the function acts on the spectrum. Here the function acts entry-wise, so I'm distinguishing it by the square bracket notation. So the problem that I have been studying, as I said, for several years, is given a function f from I to R, and given any matrix A in Pn of I, positive semi-definite, when is it that f bracket A is also positive semi-definite? And of course, we've all probably studied Walter Rudin's book in analysis, or taught from it, at least in college. And well, so Rudin, one of Rudin's well-known results and early results, well-known results, is in exactly to answer this question. And he was preceded by Schoenberg, who is also known as the father of splines, or the inventor of splines. He also founded the theory of Polya frequency functions. He studied distance geometry and so on, but he also worked on this question here. So first of all, Polya and Schur product theorem. There's a theorem by Schur, which is again I know Schur from Schur polynomials, from representation theory, but it turns out that he has so many contributions in analysis as well. So the Schur product theorem says, over 100 years old now, that if two matrices are positive, then the entry-wise product is also positive. Their usual product may not even be symmetric, but their entry-wise product is symmetric and positive semi-definite. That basically implies that the class of preservers like this is closed under pointwise multiplication. That's exactly what it's really saying. And so Polya and Zigo, using that observation, observe in their 1925 book that if you take any convergent power series with non-negative coefficients, such as a polynomial with non-negative coefficients, then if you apply that entry-wise, it preserves positivity in all dimensions for all matrices of all sizes. Okay. And are there any other preservers? I think they asked this question in their book. And so this is where Schoenberg and Rudin come in. Schoenberg said, no, there are no other continuous functions that are preservers. And then this continuity assumption was removed, and Rudin proved that result. So what Rudin said is, first of all, that there are no, so if you take any function acting on matrices of all sizes and preserving positivity, it must be of this form. But Rudin said, I don't even need to act on all matrices of all sizes. I just act on the rank less equals 3. That's so small a set in every dimension. Matrices, but moreover, I only need to act on Toeplitz matrices of all sizes of rank less equals 3. And then I automatically get that F is a power series. The other way is trivial. If F is a power series like this, then it acts and preserves positivity on every matrix. So that part was easy. That was what Polya and Zigo noted down. The converse is the really hard part. And Rudin said, I can act on a much smaller set in every dimension and still obtain this positivity. And very recently, what we proved with Alex Belton, Dominic Gio, and Mihai Putinar was that you can replace the word Toeplitz of Rudin's by Hankel, and you get the same answer. With the same rank constraint, you get the same condition. F must be a positive coefficient power series. Dimensions. When the function preserves positivity in all dimensions. Sort of recently resurfaced in applications, in high dimensional covariance estimation applications, in which case you know the dimension of the problem. You are given a very specific problem with a specific set of random variables and covariance size of covariance matrices. So why should you ask to preserve positivity in all sizes and restrict the class of functions? So it's natural to do that. Well, what is known, the problem even 70 years after Schoenberg's result, 1942. So we are almost there. Next month will be 70 years, I guess. And the problem is still open for 3x3 matrices. Even for 3x3 matrices, we don't understand the complete characterization of which functions preserve positivity. In 2 by 2 matrices, Professor Vasudeva of Punjab University actually worked this out almost 40-50 years ago. So in this talk, in the rest of these remaining 2-3 slides, I'm going to tell you about sums of powers such as polynomials, which act entry-wise and still preserve positivity. So look at this Polya-Zigo result, right? Already they say that if all the powers are positive, all the coefficients are non-negative, then this preserves positivity in every dimension. Now I want to preserve it in the fixed set of matrices only of a fixed dimension. So it's a much smaller set of matrices. So I should expect a bigger class of functions to preserve positivity. For power series or polynomials, everything positive works. So if I want a bigger set, there should be at least one power series with at least one negative coefficient, which preserves positivity on a fixed size of bigger equals 3, because Vasudeva worked it out for 2. So even for 3 by 3 matrices, find one function with one polynomial with one negative coefficient, preserving positivity. That turned out to be not known until very recently. What was known is that if you take any smooth function, not just polynomial, but even a smooth function, and you look at the first n non-zero Maclaurin coefficients of that function, the lowest n order coefficients, they must be strictly positive if they are non-zero. The n plus first, we don't know. So that's exactly the question. Can the next coefficient be negative? So the answer, so first of all, with Alex Belton, Mihai, Putina, Dominic, we answered this sort of baby case. The baby case was when the first n degrees are consecutive. So it's like saying, for 3 by 3 matrices, it's like saying C0 plus C1x plus C2x squared plus C5x to the 5. And I know that C0, C1, C2 have to be positive. Can C5 be negative? And still this 5th degree polynomial with 4 monomials only preserves positivity on 3 by 3 matrices when applied entry-wise. Can that be done? That was the question. So for consecutive initial powers, the lowest powers being consecutive, we could answer. The moment there's a gap in the initial powers, our methods broke down. So that was the case, and that's sort of the final result then. And so that is the result with tau again in the same paper. Fix integers, the first n of which are those coefficients are going to be strictly positive, and then a larger integer for which the leading order term is going to be negative. I just take that constant outside and put it here. The absolute value of that coefficient is put as a t here, or the reciprocal of that. Okay. Then the following are equivalent. Define this polynomial where I take some multiple of this. So I fix also these coefficients. So there are strictly positive coefficients, and the degrees that are fixed, t times that minus a higher power x to the m. And I want to find out at least one positive number t for which this function applied entry-wise preserves positivity on matrices of a fixed size. This happens if and only if all the coefficients are either strictly positive and this t must be bigger equals this threshold, whatever the strange looking threshold is. Okay, and there's a closed form. This is a closed form formula. So the tuples are defined here. The denominator n is the tuple of the n's. The numerator tuples are, remove one of the nj's and put in the leading term, leading degree m. And these are, strictly speaking, I said integer powers. So these are, but they could also be real powers. One can extend these kind of things to real powers as well, as we do in the paper. And that is all if and only if this polynomial entry-wise preserves positivity on a much smaller set, even in this fixed dimension. Just like Rudin said, I need a much smaller set. We said, well, also you need a much smaller set. Hankel matrices of rank 1. Okay. And so since I'm short of time, I'm going to skip this thing. But let me end then with an open question. So, okay, maybe I'll just mention the last part. The last part is the surprising bound. The surprising part is that this bound is obtained on the boundary of this cone on the rank 1 matrices. And this is where, to obtain this bound, you need to use the fact that the ratio of these guys is coordinate-wise non-decreasing, and therefore it is maximized at the biggest possible corner of the domain. It was a bounded domain. It was a hypercube or a cube domain. And the fact that these ratios are strictly increasing or non-decreasing is what we really need to use. So that's really where we get to use the Schur Monotonicity Lemma. And for real powers, we get to use the Schur-Vandermonde Monotonicity Lemma. Okay, so let me then end with this slide. I'll take a couple of minutes, sorry. So the maximization of these ratios over this positive part of the orthant reveals some tight bounds on some polynomial preservers of positivity, as I said. Okay. Because Schur polynomials are homogeneous and these guys are strictly dominating these terms, it's enough to look at the maximum value on the boundary of this cone. So it's enough to look at this part. You can ask the same thing about polynomial preservers acting on matrices with not just positive entries, but negative entries as well. And in that case, you need to upper bound this ratio of Schur polynomials over the entire cube except the origin. But of course, there's a big problem right now. What is the guarantee that when you put in negative arguments here and you evaluate this Schur polynomial as the sum of monomials, you just don't get 0 in the denominator? And so for that, you don't need to ensure this never does happen. And that actually never happens if and only if those Schur polynomials in the denominator are called complete symmetric homogeneous polynomials. And so the question I'll end with is that suppose you have these powers upstairs and the powers downstairs, such that the powers upstairs dominate the ones in the complete homogeneous symmetric polynomials. Maximize this ratio of polynomials on just this cube. And as far as I know, this is still open, and this probably can be worked out for a low number of variables, 2 variables, 3 variables. I would like to know the answers. If you think about this problem, it's also mentioned in sort of our paper, I think. It would be nice to know the answer. Okay, so that's the end of the talk. Thank you very much. These are some references.
Yeah, thank you for that. Maybe we have a time for a quick question or two if somebody in the audience or watching this online has. Those who are online can just unmute and speak or type in the chat box. Those who are here can just speak.
The online participants can raise their hand so that we can unmute them.
Oh yeah, maybe you're automatically muted. So if you raise your hand online, then they can be unmuted. Okay, well, they do that. So I was a little surprised, Apoorva, that you had some result of rooting for tuples matrices, and you did a lot of hard work to do something similar for Hankel, because Hankel and tuples are really similar, no? I mean,
yeah, they're very similar.
Hand in hand, you multiply by anti-diagonal, and so morally one should think that these two should sort of imply each other. But so what is happening here?
So actually, the way it comes about. So first of all, Hankel and tuples have one fundamental difference: is if you do the anti-diagonal thing, the Hankel things can have different entries at the top corner and the bottom corner, the top 2 and the bottom 2. But tuplets in this case are real symmetric. So they're symmetric across the diagonal. So in Hankel, this is not going to be the case.
Mm-hmm.
But the moral difference actually is that the tuplets matrices of Rudins came from looking at Fourier coefficients of positive measures on the circle. And those, if you look at the coefficients, you get by infinite tuplets matrices because the Fourier coefficients occur in a sequence, by infinite sequence. Our Hankel matrices come from positive measures, the moments of positive measures on the line. And so they are semi-infinite matrices, again, yeah, of the same kind, because for every positive measure, you get all the moments. Actually, our moments are in fact based, the measures are supported on 0, 1. So the mass of the measure dominates all other moments. So our top corner entry is S0, the mass. And then beyond that, everything else is just S1, S2, S3, S4, but those are just dominated by the S0. So that's the moral difference. We have to use completely different tools. He's using sort of Fourier analysis in some sense, and we are using harmonic analysis in some sense. I mean, these distinctions are very blurred, but basically he's using measures on the circle and we are using measures on the line. So the results and the toolboxes are different. But that said, I mean, yeah, well, the nice thing is that the proof that we gave is sort of understandable to sort of first-year graduate students, because we really use very, very low-powered machinery and just simple arguments, yeah, simple tools.
Thank you. Are there any raised hands? And, I guess not. So let's once again thank Apoorva for his very nice. Thank you.